Section 3.2, Set Operations and Compound Inequalities. I'd like to start this section off by going with a real-world example of what we're talking about when we're discussing sets. An example I have here is the two sets, the set of all your symptoms for an overactive thyroid gland and all your other set of symptoms for an underactive thyroid gland. We have this table here that shows the symptoms of each. Underactive thyroid, for example, is sleepiness, dry hands, intolerance of cold, and a goiter, whereas an overactive thyroid gland would cause someone to have insomnia, moist hands, intolerance of heat, and also a goiter is common with the overactive thyroid as well as the underactive. So with set operations, we talk about two different things involving the sets, the intersection and the union. And they mean two completely different things. When we're saying the intersection of two sets, and we can usually name the sets, in this case we can just call them A or B, or A and B. If we're looking for the intersection of those two, we write that with the name of the two sets with an upside down U in between them. And we read this as A and B. Okay, usually the way I remember it is, upside down U, it almost looks like an A. And that A there stands for and. And what that really means is when you're asked to give the intersection of two sets, is you're trying to give the elements that are common to both sets. Okay, so the intersection only includes the elements that are common to both sets. It has to be in both sets to be considered part of the intersection. Whereas the union of two sets, A and B, we write that with actual U in between them, not an upside down U, so U for union, and we read that as A or B. So what that's saying is that you want to include any of the elements that could be in set A or in set B. So it's including all the elements from both. In other words, you're combining your two sets together. So an intersection has to be what's in common of two sets, whereas the union of two sets is more, well, it could be in A, it could be in set B. We're going to throw all of those together into one bigger set. Okay. So with our example of the overactive or underactive goiter, if we were trying to look for the upside down U, which going back up here again, remember this means the intersection. We want what is in the overactive and also in the underactive. We have to look at what's common to both. So looking at our symptoms, the only symptom that's common to both an underactive and overactive thyroid is that of the goiter. So how we would write this is in set notation. We have these, open up these braces, that's what those are called, and the only characteristic common to both underactive and overactive would be the goiter. Whereas then, if you're asked to find the union of the two sets, okay, the overactive or the underactive, that's kind of how you read that, you'd have to list whatever type of symptoms happen to be in one list or the other. So what that means is every single possible symptom in the two lists needs to be written down. So we had sleepiness, the overactive on the opposite side was the opposite of that, insomnia, lack of sleep. Underactive had dry hands as a symptom. Overactive had the opposite, moist hands. I'm going to write moist for short there. Intolerance of cold and intolerance of heat. So we have to list both of those. And then the only other thing was goiter. Both had that in their list. We don't have to write that twice. It's only one possible symptom. It just shows up in both lists. So it should be in our union. So you see the difference between intersection and a union. An intersection typically is a smaller group of elements, where the union adds everything together. Alright, so you're going to have to be familiar with the symbol, the upside down U, and the regular U, meaning and or if they have a U written as intersection or union, you have to be familiar. Alright, So that's more real-world examples. How we're going to apply this to math is going to be solving these compound inequalities, either an AND situation or an OR situation. So our first example here, we have two inequalities written, and we have an AND situation. Okay? So what this is really asking you is, for what x values could we plug in so that we get something that's greater than 5 over here, and if we plug it in for x over on the right hand side, or in this other inequality, we get something that's less than or equal to negative 21. So how we solve these compound inequalities, these double inequalities, we have to solve both individually, graph them both, and then depending if we have an AND or an OR, look at those two graphs to come up with a final overall graph answer. So solving our first inequality here, negative 3x minus 4 is greater than 5. We want to add 4 to both sides to cancel out the 4. And that leaves us with negative 3x, the negative 4 and positive 4 cancel. 5 plus 4 gives you 9. And then to get x completely by itself, we need to divide by our coefficient, negative 3. And that will cancel out the negative 3's on the left-hand side of this inequality, getting us x by itself. So, remember the rule. When you divide by negative, you have to flip the inequality. So x is less than negative 3, not x is greater than negative 3. So what we can do from that is go to the graph and go ahead and graph that right away. How would that look? Well, if we had x is less than negative 3, we'd have to put a parenthesis around the negative 3 and shade everything to the left. So that's what our first inequality would look like graphically. Now solve the other inequality, 5x minus 1 is less than or equal to negative 21. So go about that the same way, starting add 1 to both sides to cancel out the negative 1 over here. That leaves us with a 5x on the left-hand side of that inequality and a negative 20 when we add negative 21 plus 1. Dividing by our coefficient 5 will get us x by itself. We're not dividing by a negative, so we don't need to flip our inequality. So x is less than or equal to negative 4. That's what that one ends up. Now the word, well, let me graph it and then I'll explain how we handle that AND situation. So less than or equal to negative 4, that means we'd have a bracket on the negative 4. And we shade everything to the left. Okay. So individually, that's what these two graphs would look like. However, we have that AND situation. We need all of the x values that would not only satisfy this graph, but also be values that would work for this graph. So the AND situation, that's the intersection, going back up to our notes, the intersection, we want only the elements that are common to both sets. So when we're looking at two graphs and we're talking about what's common to both, what we're really looking for is where do they overlap each other. Because wherever they overlap each other, that's really what they have in common. So, what do they have in common? In other words, where do they overlap? And if you look at your two graphs, well, where they would overlap each other if we graphed them on the same number line is really here from the negative 4 on to the left. because from negative 3 to negative 4, that's not part of this bottom graph. It's only part of the top graph. But what do they have in common is everything from negative 4 to the left. So the graph of what they have in common would be just that. Say we have a negative 2, negative 3, negative 4, negative 5. It would just be everything from negative 4 and shading it to the left. That's where the two graphs would overlap each other. And writing that in interval notation would be everything from negative infinity, which gets the parenthesis, all the way up to 4, but including 4 with a bracket, because over here it did have a bracket on the 4. The 4 is included here, and it's included up in that graph, so it's included in our final answer graph. Okay. So we can look at a couple more examples on the next pages. Flipping that over to the back, we have solving x plus 2 is less than 5 and x minus 10 is greater than 2. So we have ourselves another and situation, but you're going to see this turns out a little bit different. So we want to go ahead and solve these two like we did the others. It'll be a little bit easier. To get x by itself here, just subtract 2. Subtract 2 from both sides, which will cancel out our 2's. Leaves us with x is less than positive 3. Now solving this other inequality, we have to add 10 to that side and 10 to that side of the inequality. Canceling out the 10's leaves us with x is greater than 12. Okay. Once again, this is an and situation. So what we are looking for is for what numbers can we take such that our numbers have to be x less than 3, but also x greater than 12. So think about that. What numbers are smaller than 3, but at the same time are greater than 12? And if you really think about that hard enough, quickly you should come to the realization there are no numbers that would satisfy that situation. If you're smaller than 3, you can't be bigger than 12. Okay. So a little note here, there is no number less than 3 that's also greater than 12. It's not possible. So what we say in a situation like that is there's no solution. Or the set of answers, or the answer is what we call the null set. It's the set of nothing. There's no numbers in that set because there are no numbers that would satisfy that situation. So you could write the null set, or you'll see it written with a 0 with a line through it, indicating no possible solutions. Okay, so that's kind of a special case. Kind of nice though, it's a lot less work than the other ones. Now we'll look at a couple more examples. Here we're going to look at examples involving an OR statement, a union, rather than an AND statement, which was the intersection. So let's move on to this next example. Solving the inequality 6x minus 4 is less than 2x, or negative 3x is less than or equal to negative 9. So let's start doing this.